Hello everyone, today we will be focusing on Alien Dictionary with an in-depth explanation of pseudocode and expanded pseudocode accordingly, all in C++, so hope you folks enjoy. Hello everyone, today we will be going over the Blind 75 in C++, and today we will be focusing on Alien Dictionary. Now, before we get started, feel free to pause the video to be able to write down your questions and comments if you're following along. To break down our question, we need to first figure out what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output's going to be. So, to break down the question, there is a new alien language that uses the English alphabet. However, the order among the letters is unknown to you. You are given a list of strings, words, from the alien languages dictionary, where the strings in words are sorted lexicographically by the rules of this new language. Return a string of the unique letters in the new alien language sorted lexicographically, increasing order, by the new language's rules. If there is no solution, return these quotations over here. If there are multiple solutions, return any of them. Okay, let's just break down over exactly what we have. So in our input, and we can also look at the parameters up here, but also based on the question at the same time, we are given a list of string words right here. And it looks like the output is going to be return a string of the unique letters in the new alien language, sorted and lexicographically increasing order by the new language's rules, and some other cases to return. If there is no solution, return an empty string. If there are multiple solutions, return any of them. Alright, so we have those. Now, when starting off and breaking down the question, it can be confusing to be able to start because, one, aside from it being a hard problem, we are focusing more on just trying to figure out exactly, what does sorted lexicographically mean? Well, to give a breakdown on what lexicographically means, or what they entirely mean, is that the term itself, when they mean sorted lexicographically, it's really explaining about the process of writing, editing, or compiling a dictionary. And in the context of sorting, or ordering strings of characters lexicographically, it means that there is a method of organizing these strings similarly to how words are arranged in a dictionary, and this arrangement is based on the order of their individual component characters. So, say for example, if you were to sort the words apple, banana, cat, dog, in lexicographical order, you would get apple, banana, cat, and dog, because A comes before B in the English alphabet, and B comes before C, and so on. And then when you compare two words lexicographically, you start by comparing the first letter of each word if they are different. And if they are different, the word with the letter that comes earlier in the alphabet comes first. If the first letters are the same, you move to the second letters, then the third, and so on and so forth until you find a pair of letters that are different. So if you're comparing apple and ape, for example, you start with A, then P, then you move to another P, and also E when comparing between apple and ape. And because E comes before P in the alphabet, ape comes before apple in the lexicographic order. And in general, lexicographically can expand more just upon English language and literature, and I'll be introducing that in our technique that we will be focusing on, which would be called Kahn's algorithm. But I also want to be able to explain more just to help further understand and solidify the concept on a visual standpoint on what it means by sorted lexicographically. So let's say, for example, and just focusing on the English language itself and our dictionary rules, where everything is sorted alphabetically, let's say, for example, we have a list of strings called words, and this will just be our own, just for an example. Let's just say that all the words are called Adele, call, decall, elm, lap, leap, map, plead. What we'll be doing is that we're going to be doing a series of comparisons for each round. So it's like we are scanning the array first to be able to figure out the list of comparisons for every single character from every single word. So if we were to break this down, we're going to compare Adele versus call, and I'm just gonna write this process out. Then we're gonna compare call versus decal. Decal. Same thing. Anyway, and then we'll compare decal versus elm. Decal, yeah, it's decal. Sorry for the mispronunciation. Decal versus elm, and there also another thing too to note is that all the words are lowercase in the English letters. So just going on this example, and I'm gonna have these notes in the comment section as well. So if we have lap versus leap, then we have it's gonna be elm versus lap. Then we'll have lap versus leap, then leap versus map, then map versus plead. We are going to make a comparison for every single character between these two words in order for us to be able to get our output. So in this case, A comes before C, so we're going to put down A comes before C. I'm just going to write this out further. You can tag along too, but you will probably see the visual pattern that we will see. And then since C comes before D, and then D comes before E, then E comes before L, and A comes before E. Accordingly, since we are comparing, since both of them already have one letter that are the same, we move on to the next one, A, and then E. Have that comparison. Then we have leap versus map, where L comes before M, and then finally M comes before P. So lexicographically, just based on the rules from our rules of the dictionary, where everything is sorted alphabetically, our output is going to be A, C, D, E, L, M, P. That will be our output based on the rules of alphabetically sorted, which is lexicographically sorted. So this will be the exact output that we would have as a result from these list of words that we have. Now, if we want to expand this type of pattern and relationship to the words accordingly, we need to figure out what the pattern is. We know that in our English language, our pattern is alphabetically, but we don't know, since we're dealing with an alien dictionary, we don't know how all the characters are already sorted. But we already know the pattern between each of the words that they're already sorted, and our method for sorting, lexicographically sorted, is alphabetically, but the alien's dictionary is going to be different. So if we were to expand upon problem, example 1, just to go over the whole process and break down our input and output, may be confusing at first, but once we finally figure out what the pattern is, we'll know exactly what to do to expand upon the relationship of every single character from every single word. So, I'm just going to be writing this out. So if, say, for instance, in the words WRT, WRF, ER, ETT, RFTT, we know that they are all sorted lexicographically. They are sorted in order, much like in the case lexicographically. We already know in this case from each one, much like in the case of how our stuff is alphabetically sorted, these are sorted in their own process. And we need to figure out exactly just their process of why they sorted these words, and then we need to figure out what our output is going to be. So what we will be doing in this case, just based on definition of just lexicographically, is that we're just going to be comparing every single first letter that we have, and if they are the same, we compare the next one. Okay, so I'm just going to write this up here. character if both of the first characters are the same. We then move over to the second character and compare. So similar in the pattern we have for example 1 up here. And then we have for a problem example that we're going to focus on, which is sorted lexicographically. So what we're going to be doing is that we're going to be doing WRT versus WRF. Then we will do more accordingly. 2, 3, and 4. Then we would do WRF, ER, ETT, ER, and ETT. We're going off each one. Then we will do ETT and then RFTT. So when we compare the first character, they're both the same, but then we move over to the second one, both are the same. But we know that T comes before F. And then we have WRF and then ER. We already know that W comes before E. But then we know E and E. Then we know R comes before T. Comes before T. And then we have ETT. Then we have R. And since we already know from the previous relationships accordingly, we know that E comes before R accordingly. So then what we would need to do, we need to output all the used characters from our list of words, which are strings in this case as the data type. So therefore, as a result, from all the comparisons that we know and the relationships from each of the characters and the way how they're sorted, we will then get W, E, R, T, F as indicated over here. But then our question is, okay, so we can figure out between W, E, R, if we were to just scan this entire array once, we already know, oh hey, W comes first, then we have E, and then R. We've already scanned them once, but then once we go for a second scan, this is something to keep in mind, is that we are comparing the other characters as well. We know that we have R, then we have R, but then R comes before T. Look at that over here. And then we need to compare it with F as well. So if we were to come over here, well, we already know that T comes before F, and so that's why we put it right over there. And that would expand upon our relationship. And if there are any other questions, feel free to put in the comment section as well. So now, just to go over the next steps over what we will be doing, I'm going to be explaining more over exactly what Kahn's algorithm is. Now that I explain more about the whole type of concept of what they mean, about sorted lexicographically. So Kahn's algorithm is a type of algorithm that uses a direct graph algorithm, which uses a direct graph and a topological sorting technique. I'm also going to have a visual up here to help you folks be able to see the entire thing over exactly what we would do, where Kahn's algorithm, it's basically a graph algorithm for topological sorting, and then topological sorting is really for a directed acyclic graph in just a linear order. So in graph algorithms, just giving an overhead of what they are, there are two types of graphs. There are directed and undirected. The differences between the two is that the vertices where we point, our directed graph can only go in one direction linear, while undirected can go back and forth. And You may also notice this relationship at the same time for undirected graphs, and yes, trees are a form of undirected graphs. Just to put it out there if one's being able to build out their data structures and algorithms knowledge. And so, to be able to further understand about Kahn's algorithm, it's just really based on the idea of removing source nodes that don't have any incoming edges. So if we are going to be starting at the very first node that we have, there's going to be a relationship we need to find accordingly while we are moving throughout the rest of the array of our given characters that we have. And so we will use a queue eventually to store all the visited nodes, and we will also have another data structure to keep track of all the vertices which are connected to each node. And so that will be the basic idea for Kahn's algorithm of what we need. And if we were to further expand upon this even more, I would have to say the differences between the following of the two components of the directed graph and then also topological sort is that topological sorting is more of a linear operation to indicate the order of vertices in a directed acyclic graph, and that's such that each edge for each vertex between the different nodes comes before each relationship, as indicated by the visual that we have up here. And so to be able to give a breakdown of the steps of how to build out exactly what we need to do to solve this problem, I'm going to give a step-by-step process on how to do this. I'll also have expanded pseudocode in this type of problem, given the fact that this is a complicated problem to start with, and then I'm also going to post this, again, as mentioned before, in the comments, to be able to help you folks be able to understand and further visualize at the same time. So in order to actually go about this process from the following, we need to figure out how to build a directed graph from the words and perform a topological sort on the graph. It's a method used for the Kahn algorithm. And we're also going to be indicating what we will be returning. So to go over the steps or how to solve this problem is that the first thing we need to do is that we need to initialize the adjacency list to represent the graph and in degrees array, which indicate the vertices for the relationship of each character we visited. And then we're going to build the directed graph from the words and calculate the in degrees of our relationship from the characters while scanning the array. And then we're going to perform the topological sort on the graph using a queue and the in degrees array, and then we're going to check if all the nodes are included in the result, if we have visited every node, if a cycle exists in the graph. the reason why we have to account for cycles is just because of the nature of the data structure of cycles. It's just that they're like trees, except for just another case is that they're more interconnected with each other. That's just the best way of describing it. And finally, we will return the result if all nodes are included, else we will return an empty string. Okay, now to expand upon the pseudocode, given the fact that this is going to be a lengthy type of process, just with the nature of the problem that we have, I'm just going to expand upon each of the steps that we have and go step by step, and then I'm going to write out the code and need it so that way we know exactly what to do and you can follow along as well. So, just to be able to get started after we initialize, what we need to do, well, first thing we need to do is that we need to create an adjacency list to represent the graph. Then we're going to create an in degrees array with the size of 26, assuming there are 26 characters, and initialize all the elements to 0. And this part that we will have is that we will, for each word in the list of words, and then for each character in the word, we're going to initialize the in degree of each character to 0. And then for the second step that we will do is that for each pair of adjacent words in the input list, we're going to extract the first word and the second word. If the first word is longer than the second, and the second is a prefix of the first, return an empty string because it's an invalid input. And then for each corresponding pair of characters from the two words, if the characters are different, we're going to check if the second character has been visited from the first character, and then if not, we're going to add an edge from the first character to the second character in the graph and increment the in degree of the second character. Then after finding the first differing pair, we're going to break the loop as the subsequent characters of the words are not directly comparable. Then for step 3, this is where we perform topological sort, and then for each character, if the in degree of the character is 0 as an edge case, we're going to add the character to the queue. And then what we will be doing is that we're going to initialize a string to store the result. And while the queue is not empty, we're going to remove a character from the queue, and then we're going to append the character to the result string, and then for each neighbor of the current character, we're going to decrement the in degree of the neighbor, and then if the in degree of the neighbor becomes 0, we're going to add the neighbor to the queue. And then we're moving over to step 4. If the length of the result string is equal to the number of nodes in the graph, we're going to return the result string, and then elsewise we're going to return empty string. Yep, we already did that. Now, just to be able to go over the steps over what we need to do. Step 1, accordingly, we're doing is that we'll be going upon this part. I'm just going to put it right here while going over this to help you folks further understand and see it side by side. This will probably help as well. So we'll have unordered map of characters, unordered set of characters. We're going to call this a graph. This is where we create it. See, this is an adjacency list representing the graph, and then unordered map for character int in degree, and then this is where we build it. This is where we build the directed graph. So this will be for string for each word in the list of words, string and word words, for character and C word. Then we're going to have our in degree list for each character set to 0 since nothing has been added to the queue. And we're going to create the queue later. That's going to be in step 3. And now step 2. Alright, this is how we built the direct graph from the words and calculate in degrees of relationship for the characters while scanning the array. Now in the case, this is why while scanning the array, we will make comparisons of each character from each word. So for int I is going to be 0. I is less than words dot size minus 1, since we want the very last element inside of our array with I plus plus. Then we're going to compare our word 1, words I. Then we will also have the same for our second word. And now we will be doing, if the first word is longer than the second, if word 1 length is longer than the second, 2 length, and word 1. And the second is a prefix of the first. String 0 word 2 size. That's an edge case that we would have. So make sure I get this right. Word 2. We're going to return an empty string because it's an invalid input. So we already covered this edge case that we have over here. Yep, right over here. So we covered that because we ultimately saw that there was no relationship accordingly, as indicated by example 3, for example. And then what we will be doing is now focusing on the next one of characters of the 2 words now. This will still stay on the inside, actually. So for int j is going to be equal to 0. J is going to be the min of the word 1 length, word 2 length. For here, since this is how we create the for loop, then j is also being incremented because we're comparing the rest of the array and have the corresponding characters. And then if the characters are different, that means if word 1 j doesn't equal word 2 of j, that also means we all need to consider, we need to check if the second character has been visited from the first character, and that means we're going to be doing this by if graph doesn't contain word 1 of j, okay. Yeah. Count right here. Just want to be sure I got this. Count word 2 of j. If the graph hasn't been visited, then we're going to insert. Well, if that character has not been visited, we're going to put it inside. So graph of word 1 j dot insert of word 2 j, and then we're going to increase our in degree array of word 2 with its relationship. Increment that. Increment the in degree of the second character. Yep, accordingly. If not, add an edge. So this is where we add the edge, and then we increment over here. And then after finding the first referring pair, just want to be sure I got all this right before moving forward. Break. Gonna break this. Yep, that's already our first for loop that we have, and it's following accordingly. Now we're gonna head over to step 3. This is where we perform the topological sort. And the way we do this is actually now we start creating our queue of characters. Queue, and then for each character, auto, we're going to use auto and entry in degree for every edge that's already been added from each character. Yeah, it's made. Great. And then for each character, if the in degree of the character is 0, then we are going to add the character to our queue. And then string, we're going to initialize an empty string to store the result. And while the queue is not empty, C equals queue.front, queue.pop. We're going to move a character from the queue, and the result is going to be appending a character to the result string that we have. And then for each neighbor of the current character, we're going to decrement the in degree of the neighbor. I'm going to put this also right here at the same time. If we have a character in our graph over here, and then if our graph count as a character, then for all of our character neighbors, for every character of the graph, as a every single character in our graph, for each neighbor of the current character, degree neighbor, this is how we indicate that we have visited. We're going to decrement the degree, and then if in degree of neighbor is also 0, we are going to push the neighbor into our queue. This indicated we already created a character for each neighbor that we have. We're adding the character to our queue. Yep, if it becomes 0, we're going to add it to our queue. 1, 2, 3, 4. And then finally for step 4. Up here. Check if all the nodes are included, which means that we will be doing this if the length of the result string is equal to the number of nodes on the graph. So result dot size equal to the size of the degree over here equal to the number of nodes of the graph. We will return our result, and then otherwise, in another edge case, we're going to return an empty string as indicated over here. So let me just make sure I got everything right. And then also, I'm going to clean this up for you folks just to be sure that it's all clear. I know this took a lot of explanation to do, but understand the problem was the first step, so that way we could be able to move forward and understand the relationship and replicate our relationship accordingly. So, let me just check this out, and if I have any syntax errors, I apologize beforehand, just to be able to check on what we have. Yep, okay. Alright, up here. Forgot an extra bracket. Okay, let me just double check. Yep, it was just because of that extra bracket that I had. Alright, let's see if this actually runs. Sure, we got that. We got the count. We got the word. Yes. Check. Alright, it passes all the test cases. And before I do anything else, I'm going to clean this up for you folks so that way you can see entirely what we have. So that means I'm just going to move this output over here. Let's put it up with the rest. Oh my god. It's a lot. It's quite a bit. So I'm just going to put this right here. Yeah, okay. And then I'm just going to move all that stuff up here. Just to be able to put this all, and again, I'll have this all entirely inside of the comment section. So I'm just trying to figure out if I can get all the stuff in frame for you folks to be able to further see for the result. I'm going to do this. So I like how the steps are already organized for each one, because this was a complicated solution, and expanding upon the pseudocode was able to help visualize on this. I'll put this in the comment section and then entirely step by step, and then for the sake of the video, I'll just clean it all up and just put the steps accordingly. So let me just delete this. Actually, I'll just skip it right here. So put it right here. Let's put this in the comment section. And you have the steps that we have. Yeah, step 4. Okay. Because I want to get all this stuff in frame. I'm trying to see if we got it. I may not get all this in frame, but I'm going to submit it and see what happens. Alright, and it runs pretty smooth. Yeah, I'm just going to clean this up a little more. I'm going to remove all the white space, which is just good general practice. Alright, let me submit this again, clean it all up and get it all in frame so you can see the whole thing. Okay, if I can, there we go, that's better. Okay, so just to give a breakdown in terms of the space and time complexity for our following solution, is that the time complexity for our solution is going to be O of C, capital C, where capital C is the total length of all the words in the input list added together. And the reason being is this is because we might process each character in each word, but the space complexity, on the other hand, given the fact that we are going throughout the rest of our array and then scanning it a couple times, it's actually going to be surprisingly linear, even though that we have a queue contrary. The reason being is because it's going to be O of 1 or O of U, where in the case where we can consider the space complexity where, given the fact that we are only using 26 English letters, the reason being is that we are just scanning throughout the rest of the characters that we already have. accordingly when we have created our in degree list, because we just have 26 characters, which is why the space complexity is pretty efficient for O of 1. But since we are using unique characters, in this case, relative to the problem, it's going to be O of U in this case, where it's referring to the total number of unique letters in the alien language. So it can all vary and differ, but since they're all going to be lowercase English letters, it's safe to say that it will be O of 1. And so, yeah, this was Alien Dictionary using Kahn's algorithm. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. If you have any other questions, feel free to put them in the comments section. And as always, take care. Cheers. Bye-bye.